All right, students. So this question is from the topic of simple harmonic motion, and question is very, very interesting. Okay, the question says that you have a simple harmonic motion, a body in simple harmonic motion that obeys this equation. Okay, I'll just read it for you. Okay, so this is x, okay, is equal to 4 cos 1.3 t plus pi by 5. It's 1.33 t. I hope you can see it, right? The question is, at what value of t, at what time the body comes to equilibrium and is moving to the right. I hope the question is clear to you. The question is, at what time will the body be in equilibrium? It is going to move to and fro infinite number of times. There is no loss of energy. But when is the first time? Again, it will be in equilibrium starting from the initial point. That's the question, right? And it is moving rightwards, not leftward. We will try to understand this concept of in equilibrium and then moving rightward or leftward. Very, very important. Very interesting question. Stay with me and keep listening. Okay. Now let's talk about this. Okay. What is equilibrium? Equilibrium means the body is at x is equal to 0. That's your equilibrium condition. Okay. Because if you have a spring which is not stretched, right? What is the x for that? It is an unstretched spring. What is the x? When you start pulling the spring, you start applying Hooke's law, right? Which is F is equal to minus K delta X, right? K is the stiffness constant or the spring constant for the spring. Delta X is the amount of displacement from the equilibrium position, right? So at x equal to 0, you have equilibrium. When you move slightly delta x, you get a restoring force back. That's simple harmonic motion for you from the spring. This is a spring, the stiffness of the spring, right? More is the delta x, more is the restoring force, right? And when you solve this question, this equation, you get this solution. The displacement of the simple harmonic motion in this particular scenario we're trying to solve is represented by this equation. We have to find the time at which it will be back at x equal to 0, right? First time. Okay. So first let us see, if you put t is equal to 0 here, right? If you put t is equal to 0, what happens? T is equal to 0, x will become equal to 4 cos pi by 5. So at t is equal to 0, it is not at equilibrium. That has been established. So if I say my clock starts at t is equal to 0, it is not at equilibrium point anyway. We have to first establish equilibrium points. Where are the equilibrium points? So what do we do for that? We pick up this equation and we say x is equal to 4 cos 1.33 t plus pi by 5. Put x is equal to 0. Okay, we will put x is equal to 0 is equal to 4 cos 1.33 t plus pi by 5. Okay, which means cos inverse 0 is equal to 1.33 t plus pi by 5. I hope so far so good, right? It is clear in your mind as to what are we trying to do. We are saying first we will establish the displacement is 0, which means it is in equilibrium. Then we will see in the subsequent motion, when does it come at equilibrium position at t greater than 0. The first when it and moving towards right, which is very, very important condition in this question. Okay. Now, when is cos inverse 0? cos inverse 0 is essentially n pi by 2, right? Which is a general equation for cos inverse 0. Okay, so I put it as n pi by 2, and n in this case comes out to be plus minus 1, plus minus 3, plus minus 5, right? So if you have a cosine graph, like this, this is what happens, right? So this is, and this is a point which is pi by 2. Then you have another point which is, so pi by 2, it is 0, cos pi by 2 is 0, and then pi by 2, and then 3 pi by 2. And on the left hand side also of the cosine graph, therefore I have written plus minus 1. So this is a general equation. So this makes the question very interesting. It has a lot of trigonometry. Remember, simple harmonic motion has a lot of knowledge of trigonometric function like sine and cosine. It's all about sinusoidal functions. So I hope this is making sense to you. Now what I do is I put, so let me get this t equal to something, right? So let me just resolve this equation, and what I do now is this. Okay, so let's say I find some space. Let me find some space to write. Okay, so this is where I will write now. So what I do is I put 1.33t is equal to cos inverse 0 minus pi by 5. Okay, this is what I got because I want t is equal to something. Okay, so okay, let me just rub this off and rewrite this. So t is equal to 1 upon 1.33 divided, I bring it here, and this is n pi by 2 minus pi by 5. Okay, so now I can put n is equal to 1 and n is equal to minus 1 to decide the time. Okay, so far we have been able to get an equation of t. We have put this equal to, I can put n is equal to 3, and I can also put n is equal to minus 3. N is equal to 5 minus 5. Those are the times at which it will be at x is equal to 0. We are very sure. We have to find the first one, right? So let's talk about that. How do we know that the body is in equilibrium and is going rightward? Let's take a derivative of this. Okay, so the derivative is dx by dt is equal to v is equal to minus 4 sine into 1.33 and t, okay, plus pi by 5 into 1.33. So I've applied the product rule on the sign, and you can see, right, I'm getting a negative sign, which means how do I make this velocity to be positive? That's the question, right? What are the quadrants in which it will remain positive? First quadrant. Okay, so if I put t is equal to so this particular expression has to be made negative, right? Because if the value of sine comes out to be negative, only then this expression will become positive. So the argument of sine, which is this, has to be coming out to be, so it cannot be the first and the second quadrant. Okay, it cannot be first and second quadrant, it has to be the third quadrant, which means the total value of this should be between pi and 3 pi by 2, right? In the third quadrant you will have sine to be negative, because in the first two quadrants sine is positive and I want these to be negative. Now when it comes to our situation, what we want is that the displacement has to be 0 there, and the body should be moving rightward, right? Which means the velocity should acquire a positive sign. So if I look into the options I have an option of n pi by 2. Should I put n is equal to 1 or should I put n is equal to 3? If I put the value of n is equal to 1, I will get 1 upon 1.33, and this whole thing, right, will become what quadrant? This will become pi by 2 minus pi by 5. What quadrant is this? Because this will get substituted here, right? This quadrant of will become pi by 2 minus pi by 3 is the first quadrant. So not good, right? So we don't want this. Let's use the second one. So this is 1 upon 1.33. This is 3 pi by 2 minus pi by 5, which is this 1 upon 1.33, and this is 270 degree minus 20 degree is equal to 1 upon 1.33, 250 degrees. This is perfect. This is in the third quadrant, and we want this whole value to be in the third quadrant. How is this possible, right? So if you see this equation here, the sum of these two, right? The sum of these two should be in the third quadrant. Okay? Talking in a reverse manner, the sum of 1.33t plus pi by 5 should be between pi and 3 pi by 2. So you can do it either ways. You can either take this equation, get it back, and look at this equation, right? So if I put this equal to 3 pi by 2, right, then this thing will be where? This whole argument, which is the angle theta, will be in the third quadrant, and we will get a value like 250 degrees, which is very good. So what we do, t is, so we will select n is equal to 3 instead of n is equal to 1, because that n is equal to 1, right? If I put n is equal to 1 here, this is what I get. I will get this as pi by 2. Okay, I will get this as pi by 2 is equal to 1.33t plus pi by 5. Okay, so if I see this, this is coming out to be in which quadrant? First two quadrants, right? Which is something we don't want. We want this particular thing to become negative, so that the velocity also becomes, sign also becomes negative, and this negative and negative combine together to give you a positive. So velocity should be rightward. That's a point. I know it's a difficult problem to envision and envisage, but that's the way it is. Knowledge of trigonometry, nothing more than that. I haven't done anything special. Okay, so t therefore will be given by, if you subtract these, you will get LCM as 10. This will become 15 pi minus 2 pi, and this is t is equal to 13 pi upon 10 is equal to 13 into 3.14 divided by 10 multiplied by 1.33. So if you multiply 13 into 3.14, right, 13 into 1.4, it gives you around 18.2, right? So this is 13 threes are, sorry, it will be, let's multiply this, right? So this is 13 multiplied by 3.14. So 3.14 into 13, 3 fours are 12, 4, this is 9. So this is 4. This is 3, 1 fours are 4, 1 ones are 1, 1, 3. So you get 2, 8, 0, and 1. So this is 40.82. So you have a 40.82 in the numerator, and you get around 13.3 in the denominator, right? So let's divide 4082 divided by 133, right? So 433 into 3 will give you 9, 9, and 3. So this is 1890, and you will get right, 399, sorry. So this will be 399. This will, if you subtract these, what you will get, and this will become 9, this will become 2, so 3.0 and 133.7, right? 7 threes are 21, 23. So roughly around 3.07, right? So what you get is t is equal to 3.07 second. This is a time at which the body will be moving towards right and will be, in the equilibrium position for the very first time. Now, in the second, right? So because n was chosen to be 3. So if it is n is equal to 1, at that instant the velocity is leftward. At n is equal to 3, the velocity is rightward. And you can find the rightward velocity by putting the value of t here to be this. Okay, what we found out to be 3.07. You can solve this, you will get a velocity which will be positive. If you put the lesser value, which is n is equal to 1 there, the velocity will come out to be same but negative, the value wise. Do this calculation also to do a cross checking of the concept, whether the logic we have used to solve this problem makes sense or not. So I hope you enjoyed this video. I have a playlist of simple harmonic motion. I am trying to improve upon it and put some more great questions. But if you want to learn the basics, fundamentals of simple harmonic motion, you want to understand conceptually what it is all about, it's already there. I will add some more numericals for your benefit. Thank you very much.